In this lesson, we'll be going over how to draw Lewis structures of molecular compounds. Unlike ionic compounds, which are quote-unquote bonded together by electrostatic attractions from the positive and negative ions, molecular compounds are bonded together through covalent bonds, where two electrons are shared between two atoms instead of the electron being fully transferred from the metal to the nonmetal. Let's look at carbon tetrachloride for an example. See how in the middle, the carbon is bonded to 4 chlorine atoms. What sets carbon apart from chlorine, for example, is that carbon has 4 valence electrons, the 4 electrons on its outermost electron orbit. Each one of these electrons can combine with another electron shared from one of the chlorines to give both atoms 2 electrons. These are called bonding electrons. Chlorine, however, only has 1 bonding electron, seeing as it has 7 valence electrons. What this means is 6 of these electrons will make up 3 lone pairs, but the last one is used as a bonding electron to form bonds with the central atom. As you can see in this molecule, each atom has a full octet. That is exactly what we're looking for. All of the atoms must have 8 electrons, or else it's incorrect. If we were to count it up, we can see that there are 4 bonds around carbon. If each of them count as 2 electrons, then that means the carbon has 8 electrons. And for all the chlorine atoms, they have 3 lone pairs of 2, equating to 6, plus the 2 from the bond. So everything is stable. This molecule is very easy to draw, but that doesn't mean that all of them are this easy, which is why I come up with a method to draw any sort of molecule. Let's try this next one that may be difficult without my strategy. The compound in question is dinitrogen trisulfide. I wouldn't even know where to start to draw this molecule. It's not like the last question, where everything is practically handed out to you. There are 4 chlorines that each can only make 1 bond, and so conveniently, the carbon has the ability to make 4 bonds, which is why we need to start by counting up how many electrons there are in this compound. First, we know that we have 2 nitrogens, and each of them has 5 valence electrons. We also have 3 sulfur atoms, which each have 6 valence electrons. 2 times 5 is 10, plus 3 times 6, 18, which equals 28. That means that we will have 28 electrons, including the 2 from bonds. The next thing we want to calculate is the number of bonds that will be holding the compound together. Instead of using the number of valence electrons, we're going to use the number of valence electrons required to bring the atom to a full octet. So for nitrogen, it would be 3, and for sulfur, it would be 2. So 2 times 3 plus 3 times 2, 6 plus 6, 12. And then we're going to divide this number by 2 because there are 2 electrons in a bond, giving us 6 bonds. Now we have something to work with. We know that there's going to be 28 electrons as well as 6 bonds. Seeing as we have 2 nitrogens and 3 sulfurs, let's do sulfur, nitrogen, sulfur, nitrogen, sulfur. And let's connect everything with 1 bond. So now we have 1, 2, 3, 4 bonds. Where can we put the other 2? Taking a look at the central sulfur atom, it already has 2 bonds to the nitrogens on its left and right. We know that sulfur has 6 electrons, meaning that 2 of them are bonding electrons. So we can have 2 bonds, but not more than that. What about the nitrogens? They each have 2 bonds. But since they have 5 valence electrons, that means that they have 3 bonding electrons, meaning they could each use 1 more bond. Let's confirm by looking at both of the sulfurs on either side. And as you can see, they each only have 1 bond, but they are capable of 2. So we can add both of them there. Now let's put the lone pairs where they belong. This sulfur all the way to the left has 2 4 electrons from those bonds, so it only needs 2 more lone pairs. Nitrogen has 2 4 6 electrons from the bonds, and now it only needs 1 lone pair. And then this sulfur in the middle has the bonds on its left and right, so we can add a lone pair on its top and bottom. We can add another lone pair on the nitrogen and 2 more lone pairs on the sulfur. So now let's confirm with the numbers that we are given. we do indeed have 6 bonds, and we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28 electrons, including the bonds which count as 2. And that, ladies and gentlemen, is how you know if you've done a molecular compound correctly, and it looks like we just have. Let's take a crack at another one. Again, let's count the number of electrons. There are 2 hydrogens which each have 1 valence electron. There's a carbon which has 4 valence electrons. And there are 3 oxygen which each have 6. 3 times 6 is 18, plus 4 is 22, plus 2 is 24. Now for the number of bonds, there are 2 hydrogens and each needs 1 electron to be stable, plus the carbon which needs 4, plus 3 oxygens which each need 2. 3 times 2 is 6, plus 4 is 10, plus 2 is 12. 12 divided by 2, once again we have 6 bonds. Now to get drawn. A good tip. We're very lucky to have carbon for this example. Carbon is a great central atom, seeing as it can make 4 bonds and satisfy the octet of many atoms around it. So we can draw that in the center. Now what would happen if we bonded the hydrogens to this carbon? Well, that would be our first 2 bonds, and both of the hydrogens would be stable. And now for the oxygens, the only place that we have is to place it above and below the carbon. So let's place 1 above it, 1 below, and then another oxygen above this oxygen. Now counting up the bonds, this is only 1, 2, 3, 4, 5. We need 6. Where can we add another one? Well, we can't add any more to the hydrogens because they only require 2 to be stable. What about this oxygen on the bottom? Well, then that would overload the carbon, as it can only have 4 bonds, and this would be a 5th one. What about between these 2 oxygens? Well, then that would make this oxygen have 3 bonds, but it can only have 2. We've covered everywhere that we can put an extra bond, but this structure just cannot work, so let's erase everything. Another tip, always draw hydrogens last. So let's restart. We have carbon in the middle, and now let's attach all of the oxygens. And maybe we can give each of them 1 bond. That uses up 3, carbon can have 1 more bond, and so we can attach this hydrogen for the last bond for the carbon, and another hydrogen for this oxygen on the left. And now I count 1, 2, 3, 4, 5 again. Well, we can't put any more on these oxygens or this hydrogen, as carbon can't have 5 bonds. And we can't put another one on this hydrogen, as it only requires 1. So instead, why don't we move this hydrogen to attach to this other oxygen on the right? This opens another bond that we can put for the carbon, and the only possible place that we can put it is to this oxygen on the bottom. And now I count 1, 2, 3, 4, 5, 6. These oxygens will now each have 2 lone pairs, 2, 4, 2, 4, 2, 4. And then let's confirm by counting the number of electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And once again, we have drawn a perfect molecular compound. So now we've drawn Lewis structures for regular molecular compounds. But what about the polyatomic ions? Well, just a heads up, these ions do not follow the same laws as normal stable compounds, meaning we can forget about how many bonding electrons and things like that. In terms of the strategy for counting the number of electrons and the number of bonds, there is only one slight modification, and that's because of the ionic charge. In ionic compounds, the metal gives away an electron. It then becomes a cation. A cation has a positive charge because it got rid of 1 negative electron, meaning that the nonmetal that receives it becomes an anion and has a negative charge because it gained 1 negative electron. Taking chlorate, for example, which has a negative 1 charge, it has an extra electron, making it a polyatomic ion. Let's start by counting the number of electrons. First, chlorine has 7 electrons in its valence shell, and then we have 3 oxygens which each have 6 electrons in the valence shell. And now because this ion has 1 extra electron, we add 1 to the total electron count. And so 3 times 6 is 18, plus 7 is 25, plus 1 is 26. And now for the number of bonds, chlorine needs 1 to have a stable 8, plus 3 oxygens which each need 2. And now here we are not going to add the extra electron, but rather subtract it, seeing as we are adding this extra electron to one of the lone pairs and not one of the bonds. Trust me, this is all for the better for the structure of the polyatomic ion. So now we have 3 times 2, which is 6, and then plus 1 minus 1 cancel out, and so 6 divided by 2 for 2 electrons in a bond gives us 3 total bonds. So now we need chlorine as the central atom, surrounded by these 3 oxygens, which each have a bond. In terms of adding lone pairs now, each of the oxygen will now have 3, adding up for 2, 4, 6, 8 with that bond for each of them. And to make the chlorine have 8, we will give it its own lone pair. And finally, since this is an ion after all, we have to put square brackets along with its charge. Now let's refer back to the number of electrons and bonds that we need. There are indeed 3 bonds, and counting up the electrons, there are 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. And each atom is stable, and the ion has the correct charge on it. Let's try another one to get it to really sink in. How about nitrate? For the number of electrons, nitrogen has 5 valence electrons, plus the 3 oxygens, which each have 6 valence electrons, plus the 1 extra from the negative charge, meaning that the nitrate has an extra electron. And so 3 times 6 is 18, plus 5 is 23, plus 1 equals to 24 total electrons. And then finally, for the number of bonds, nitrogen needs 3 electrons, and the 3 oxygens each need 2 electrons. And then finally, we are subtracting 1 electron as it is going to be a lone pair and not one of the bonds. And so 3 times 2 is 6, plus 3 is 9, minus 1 is 8. And 8 divided by 2 is 4, meaning that there's going to be 4 bonds. So let's see, we have nitrogen as the central atom, as well as the 3 oxygens surrounding it. And let's start off by giving each oxygen 1 bond. 1, 2, 3. And where can we put the last one? Well, the oxygens are not connected, meaning that we can only give this last bond to one of the oxygens. Now this leaves the nitrogen with 4 bonds, meaning it has 8 electrons, meaning it's stable. This oxygen that has 2 bonds only needs 2 lone pairs, while the other 2 need 3. And so counting our totals, we have 4 covalent bonds, and now 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons. And last step, almost forgot, add your square brackets with the negative charge. With this strategy, I am confident that anyone can master the skill of drawing Lewis structures of molecular compounds, whether they're regular molecules or polyatomic ions. If you've made it this far into the video, chances are you're learning a lot and enjoy the content. So if you don't mind, consider subscribing, as it shows me that you like what you see, which helps me post more videos. Anyways, that's all for now. I hope you have a wonderful day.